the next chapter, I believe, which is really focusing on these secondary parameters. This doesn't mean they're less important. Everyone is special. Everyone, in my book, is a primary parameter. Well, Rich, how did you feel about the intro music?
It made me want to get down and boogie.
Okay.
And I do like to boogie.
Mission accomplished. You're welcome, world. So I'm sitting here with Dr. Richard Vath, who's joining us. And as a recap, he's here. He's one of the co-authors of Hitchhiker's Guide to Leaf Level Gas Exchange. So, Rich, why don't you go ahead and introduce yourself?
Yeah, thanks, Seaton. I work as a field application scientist here at LI-COR. I lead a small team of scientists whose primary role is to be sort of the customer-facing scientists at LI-COR. So we spend a lot of time training people. So we do sort of condensed trainings. We call them workshops all over the world, actually, on various product lines, including the photosynthesis instruments that LI-COR produces. And then we also have a role in product development as well. So as you well know, spent some time working together.
I'm sorry.
We work with the product managers to make sure that what the solutions that get produced by LI-COR are sort of meaningful for what the scientific community wants, because we're out here talking with scientists all the time and trying to figure out, well, what's the next thing that people need to further the way that we understand the world.
That's awesome. So that's a pretty busy title. You're doing a lot of different things here. Maybe break down like how your background shaped you into that role. Like what led you to coming back and do what you do?
That is a good question. Do some personal reflection. I usually do that in private, but
yeah, no, it's public. Be deep.
Well, I guess so. Background-wise, how I got here. So I've worked at LI-COR for an aggregate about 7.5 years altogether. That was sort of split into two distinct phases of life. So when I first started working for LI-COR, I was actually a marketing intern for about 7 days, and then I moved to the sales group, and I was in my undergrad at this time.
I still can't get over this 7 days thing. Go ahead, I'm sorry.
7 days for 7 listeners. No, I was on the sales team, and I was working on my undergrad at the time, and I was studying soil science. And so I thought, well, these things are related, right? We make some instruments that have something to do with soil, although at the time I didn't know a whole lot about what that meant from a scientific perspective. But
sure.
But over those years, so then I was in sales for probably 5.5 years. And over those years, I really enjoyed the technical aspects of the instruments and learning about the theory behind how we measure the things that we measure. It wasn't just like the interaction with customers were nice, but I honed in on sort of the scientific and the engineering side of things. That was very interesting to me, and something that I didn't have a formal education background in, like especially the engineering side of things.
Sure.
So that was super neat to learn about. I enjoyed it a lot. And then I was going around in sales and visiting with different labs and things, and I was meeting people, and I was like, well, this seems like a pretty cool life too, this research thing. And so at some point I decided I don't really want to be in sales for the rest of my life, because it made me sad sometimes, as these things do.
Yeah.
And so I thought, well, maybe I should do something different. And I like instruments and I like science, so maybe I should try to go to grad school. Oof. And so I left and went to grad school. I studied plant physiology, so I focused on sort of dynamic photosynthetic, the interplay between photosynthesis and photoprotection under dynamic light conditions, specifically in sorghum, and looking at like genomic variation within the sorghum genome in response to dynamic light.
Very cool.
And then somehow ended up back at LI-COR, and now I'm this field application scientist guy here. And it turns out that this combination of sales and science in my career history has allowed me to be able to speak reasonably competently with people.
Oh, hold up. The listeners will be the judge of this.
This is fair. And I'm sure they will have many angry emails when we're done here, which I hope we're going to read off some emails at the end, by the way.
No, you're doing great.
But anyway, I can speak with people about the instruments and sort of the interaction between instruments and the things that they want to measure, which is so this role has been a good fit in that regard, and that's sort of how I got here.
That's great. Yeah, I do think it's a good fit. You, other than what I'm currently doing right now, most people here speak quite fluently, very clearly. You always do a great job, and I think Rich typically sells himself short on a lot of his skill sets. But before we get a little bit more into the podcast and really the book, I was wondering if you would be willing to share a fun fact about your time, either your first go around at LI-COR or right now, that you wouldn't mind sharing with the entire world. And if it were to be funny and make fun of Jason in some way or another, that would be bonus points.
Ooh, I love making fun of Jason.
Yeah, just one though.
Okay.
We don't have that much time.
I mean, the more recent ongoing fun fact about Jason's life is that now that he directs some research and scientific development at LI-COR, his ego can no longer fit into various spaces that he normally needs to go into, like vehicles and rooms. And so I hope that he doesn't actually listen to any of this podcast, because it may become clear at some point that some people at LI-COR think highly of him, and I wouldn't want him to like further have issues with this ego packing issue.
Yeah, we can't have that.
Yeah, so that's my fun fact for somebody at LI-COR. It's not about me.
I'll take it. That's still a fun fact. Yeah, that's great. Thank you for breaking down your role, your background, and what you do here. And I asked the same thing to Jason. What was your role in this book? Right, like why did you agree to write this book? And how did you get roped into doing this podcast?
So as Jason mentioned in the first episode, this sort of grew out of a discussion based around workshops, right? So he used to give these workshops all the time, introducing generations of grad students to a more complicated way of life. And now I've taken the torch from that process, and I continue to do the same thing. We have a very similar way that we look at the purpose of the workshops and how we go about making measurements both accessible and ideally improving the quality of measurements that people make. Because as I think he probably alluded to in the beginning, these instruments just put out numbers no matter what you do.
Sure.
And so knowing something about how you get to these numbers is a key part of like getting something useful that actually tells us something interesting about the world. And it's not just a bunch of mumbo jumbo.
Yeah. Well, I don't want to brag, but I've collected a lot of bad data. So.
Sure. Yeah, I believe it. I look at you and I see that. And it's because this book wasn't available to you when you were in grad school.
If I could turn back time, Rich.
It's a good song.
It is. Classic.
So, yeah, when Jason told me, so when I came back to LI-COR after grad school, Jason had mentioned that he had started to work on this book and outlined sort of what he was hoping to accomplish and the way he was going about it. And I thought, that's a swell idea, buddy. And then it sort of sat at that state for a while. I think for both of us. I think he had quite a while where he just didn't have time to write for a bit. But then he ended up asking me if I wanted to collaborate with him on it, because I think with discussions over the months after that, after me returning, we started to see that we do have really similar ways at looking at how this information should be presented to people. And this way we can also help sort of split the burden of writing a fairly large tome between a couple people and maybe expedite this process a bit. And so that's how I sort of got into the writing portion. So I joined a little late in the game.
A little late,
but I reviewed all the chapters that were already written up to that point.
Basically the same thing.
There were so many typos.
Oh, I can't wait for him to listen to this. So that's kind of like his vision, and maybe it sounds like you had a shared vision, but like, what is your specific hope for this book for those who are listening right now or those who come across it later?
Sure. I hope that somebody picks up this book, and of course I hope that it helps them make better measurements. Like, sure, that's the key to all of this, right? But I also hope that they find it enjoyable to read. Like, we made some effort to make it enjoyable. And though I wrote some jokes in that were edited out by my co-author, I still think it's a pretty funny book. And yeah, I think that helps in the accessibility quite a bit, and just something that it's not just a textbook. There are some great illustrations, as we've alluded to, and now you can download the first episode or the first chapter online.
Yes.
So you can get into some of these great illustrations. So I hope that people have fun, and then it helps them be better about making measurements and also understand the world a bit from a sort of physical principles approach. I think we do a really good job at starting from a very, just from the very beginning of various physical processes that go into making these measurements. We do a great job of starting at the very beginning, a very accessible way to somebody who you don't need to be a physicist to understand these things. Sometimes people try to teach you these things and you see a big line of equations and you just sort of shut down, or at least I do. I have.
Definitely do. Yeah.
But if I'm presented with things from a very early first principles derivation approach, it becomes a lot easier to follow. And at least in the way that we understand the world, we as scientists and humans, this is a really accessible way to start to understand phenomena that are happening both around in the world around us and in the instruments in our measuring systems.
Yeah, that's well put. Way more eloquently than I would have said. It is very approachable, right? It is a humorous, approachable way, and it gets increasingly complicated, but not to a point where I don't think people should be frightened. I think this is a gateway manual for LI-COR plant physiological products.
This is LI-COR's second gateway drug. It doesn't get increasingly complicated necessarily. I think the first section of this becomes a snowball of complication. And then for the biologist reading this, I think after the snowball of complication, which the first section of this book revolves around the actual measurement itself.
Sure.
The latter half of the book has a lot more biology and what to expect when you make measurements, which I think will come a little quicker to the biologists that read this, which hopefully there will be many.
Yes, I agree. I think there's a lot of questions that biologists will have historically asked that will hopefully be clarified with the understanding of the physics, the engineering behind everything. You said this was LI-COR's second gateway drug?
Yes. Well, we're not a well-known drug producer, but part of the company actually is. But once upon a time, we sold a lot of light sensors. We still do, actually, as far as I know. And there was a joke in sales that this was sort of the gateway drug to LI-COR, because somebody would buy a light sensor, which is a relatively inexpensive thing to purchase in the grand scheme of things. And then they're sort of exposed to like, oh, look what else I can measure from this company.
So let's put that aside and maybe get into the nitty gritty, right? So last week in episode 1, or 2 weeks ago rather, Jason and we kind of went through the preface. What do you say?
I agree with preface.
You say preface?
Although I thought immediately prima facie, and that came up eventually, but it took longer than I'd hoped.
Oh boy, yeah, that was flagged in my Google search. We've got preface, and then really the three main parts of the book, right? The instrumental understanding, thinking like a plan, and conceptual framework of the instrument itself. But today, what are we going to be focusing on?
Yep. So in chapter 2, we move from this sort of instrumental understanding into how do we get some of the numbers from this instrument? How do we get to these calculated numbers based on the things we are measuring, right? So Jason explained how an ERGA, an infrared gas analyzer, works in a reasonably understandable way. And now, what do we do with these densities that we get, these concentrations, just kidding, mole fractions that we get from the ERGAs? How do we make something that tells us something about what's happening in a chamber-based system? Notice there that I say what's happening in a chamber-based system, not what's happening in a plant. We'll get to that.
Yes.
But not right away.
I love it. Very specifically vague.
It depends.
Yeah, it depends. Wouldn't that be a great t-shirt?
And podcast title.
We'll see now, though. We'll see what can be done. So you touched on this just a moment ago, right? We aren't measuring photosynthesis. We're not measuring what the plant itself. We're measuring lots of other things, right? But we're at the spectrally unique fingerprints with an ERGA, and I think that for those who download this chapter, which I think everyone should, there's a pretty good car analogy that I actually quite like, and maybe you could just kind of walk people through that, because I think that clarifies different types of gas exchange systems.
For sure, especially for our older listeners or people who like to use soil gas flux systems, this will make a lot of sense because there are a couple of different types of gas exchange systems. One of which is a more traditional, sort of the initial way that these measurements were made, called a closed transient system. And Jason uses the analogy, and he included a certain vehicle that he once upon a time owned, and he drew a little leprechaun in there, which is apparently him. And another vehicle that has windows up and his windows are down. And he uses this analogy to describe these two different gas exchange systems. One, the closed transient, where we measure some change in concentrations over time in a closed system where we're just recirculating air, and use the rate of change of those mole fractions, I should say, not concentrations. We use the rate and change of those mole fractions to tell us something about what is the rate that whatever's in the chamber is taking up CO2, perhaps giving off water vapor, transpiring. And second, we use this windows up and windows down situation to describe an open gas exchange system, which is what more modern systems are based on.
Sure.
Where instead of recycling air or recirculating air, we just continually flow air through a chamber. And we can use a couple of different types of mass balances to say something about what's happening in the chamber if some important assumptions are met about the chamber conditions and the air tightness of the chamber. If we know what goes in and we know what goes out and how quickly it did that, that can give us some idea of if there's something in the chamber changing those concentrations, how quickly is it doing that? So what's the flux of this material in the chamber?
What the flux is going on? Yeah. So you mentioned going from closed to more open systems. Why did that change happen? Why is that a benefit, or how do we arrive at that design?
So it turns out that this closed system, it presents a challenge in that there is no way with a continually recirculating air stream in a closed chamber to ever expose a plant that's actively photosynthesizing to a steady condition, right? So you can never see what it's doing at any given steady environmental condition because it is constantly affecting the same air that's being used to measure what it is doing.
Sure.
Right? So there are some useful things that we can take from this related to calculating gas exchange and understanding that basically the rate of change of a concentration of gas, basically the rate of change of a mole fraction of gas per unit time, times the ideal gas law tells us something about sort of dynamic changes within this chamber-based system. But we use this we introduce the topic this way because now we have introduced this dynamic mass balance in the newer photosynthesis systems that allows us to utilize the principles from this closed system and the open system together to say something about what's happening in a chamber that's just biology. How can we solve at any point for whatever I'm seeing is just biology and not instrument? Because that's a big part of these workshops and using these instruments is understanding when is what I'm looking at the thing that I think is what I'm looking at, right? Which effectively means when is what I'm looking at something that's representative of the plant and has no artifacts from just the way that I'm using this instrument or have configured the instrument.
Right. And so this dynamic approach is I think in the book it's mentioned as a hybrid, as this mixture of the two that is far more beneficial. Mm-hmm. Is that how much more difficult is that to accomplish with our system?
Well, because the instrument that we make, and I should say while we discuss this, that the book is written in an instrument agnostic manner. Like, of course, there are some LI-COR logos in here, and there's some imagery of LI-COR systems.
We got to keep the lights on.
All illustrated, no photographs in here. Don't worry, it's not a marketing brochure. But it's written in an instrument agnostic manner. But we do describe the way that LI-COR goes about these approaches. And the way that we do this is not more difficult than a sort of traditional gas exchange system or just a steady state or an open gas exchange system with no dynamic calculations because of this is all from an engineering perspective, the way that we've designed the system in order to be able to characterize its own sort of dynamic behavior in the absence of leaf. And so basically we can set up the system with the appropriate utilities that are built into the instrument to characterize time constants that go into the measurement and then apply that to a measurement with a leaf in the chamber and always be able to solve for just what is leaf. And that allows not only for higher quality data, for example, for new users, it allows an opportunity to sort of get a double check that what you're seeing is just biology and that biology is at steady state, because that's a whole separate question is whether the plant in the chamber is at a steady state And for a lot of the things we do, we want that to be the case.
Sure.
But it also allows us to make some measurements faster, right? Because then we can continually measure change over time. And certain types of measurements, we really want to do that.
Yes.
And so if we can get more data and do it way faster, that's good for everybody, because then we can have bigger experiments and we can know more about our treatments and our controls and whatever we're trying to look at. We can know more about the world per unit time.
Per unit time, not concentration. So we've got open, we've got closed, we've got hybrid dynamic systems, but like, what are we actually measuring, right? We've talked about this unique spectral fingerprint, but with these types of systems, there's kind of this discussion of derived parameters, derived data. Maybe break some of that down so we know what's actually being measured and what is being derived.
Now, this gets into some of my favorite parts of this process and training for these types of measurements, is that we only measure temperature, right? Everything's a temperature
everything
sensor.
Is a temperature sensor,
right?
Yes.
We only measure the density of some gases before and after a chamber. And we make some measurements of temperature, leaf temperature, and temperature around the leaf. Measure the light intensity that's coming into a chamber. That gives us some ancillary info, some context around our measurement. So we only measure a few things, right? We're measuring some light intensity, some temperature, and some gas concentrations. And then we use this whole cascade of derived parameters based on those measurements, and a flow rate, of course, too. We need a flow rate. We use a whole range of derived parameters from those select few measurements to make a whole bunch of inferences about like biology inside of a leaf. Right? We don't have a sensor in a leaf. There are sensors of some things that can go inside leaves, but we're not doing that with the gas exchange system.
Yeah, don't get excited. That's not,
Sorry, maybe version 3.0, but not right now, right? And so this goes into what's measured and what's not, right? We don't measure leaf area with the instrument, but we need to know something about leaf area, because all these fluxes that we described, they're all reported on a scalar basis, right? A standardized basis. So usually in the case of our leaf level measurements by leaf area, this could also be done by mass, depending on what type of material you have in the chamber.
Sure.
So we need to know something about leaf area, but then we need to know these flow rates and concentrations, and from that we get everything else, that the numbers that come up on the instrument. Like the majority of parameters on these instruments are calculated parameters from a select few measurements.
Yeah, that is. It's pretty remarkable what can be done with the number of sensors that we have, especially if anyone looks at the data output in Excel from a 6800, 6400. The amount of information from a few sensors is pretty remarkable. There's a mention about cross calibration in this, and I was wondering if you could, if a reader comes across that might be a little confusing for someone. So maybe could you break part of that down?
Sure. At the risk of spoiling too much book, or like how does an ERGA system, a leaf level gas exchange system work? The reason we need some cross calibration is because we use two independent ERGAs to tell us something about what's happening in a chamber, right? This is an open system where we have a measurement before the chamber and after the chamber. We can call these reference and sample gas concentrations or mole fractions. So you might hear like CO2R and CO2S for reference and sample before and after the chamber. Right, and if we're using these, and dear listener, if you want to figure out how we actually calculate something from these, just read the book about mass balances, chapter 2. If we're using these two separate analyzers to tell us something about what's happening in this chamber, we need to be sure that if these two electronic devices, which have their own sensitivity to CO2 concentrations, right, they have their own calibration functions, they have their own sensitivity to time and a little bit to temperature. If these two separate devices see the same air, that have the same concentrations of gases, that they say the same thing, that way, to the greatest extent possible, we can say if they're seeing something different, that difference is because there's something happening in the chamber that's affecting the airstream flowing between reference and sample. Okay, so we need some way of cross-calibrating these. We call that a match in our systems. Other instruments might use other names for this, but it's effectively diverting the airstream so that the same air flows through the reference and the sample analyzers near simultaneously, or at least with nothing affecting what's happening between those two measurements.
Yeah, a very important process.
Match early and match often.
That's
what we say.
Another t-shirt idea. So match early, match often. From here, we kind of move into the next chapter, I believe, which is really focusing on these secondary parameters.
Hmm.
This doesn't mean they're less important. Everyone is special. Everyone, in my book, is a primary parameter. But what do we mean? What is the book trying to get across to the readers?
Well, if I had to make one broad overview, it's sort of going back to what I mentioned before. There's a whole bunch of stuff that we're calculating here. And so knowing that it's calculated and heavily derived can help you diagnose when you're getting reasonable versus non-reasonable information. So what leads into this chapter 3, at the end of chapter 2, we go into some discussion of uncertainty in parameters that we're measuring. Okay, so
Right.
this gets into like instrument performance specifications, things like this. And I say that I don't want it to bore the listener. It's not too in depth into like precision and resolution and stuff. Jason already bored you enough with that as it is.
Agreed.
But I actually like this uncertainty discussion. It's one of my favorite things because we get these instruments. I'll place myself as a young grad student again. We get these instruments and somebody hands it to us and says, go measure photosynthesis. And we go out and do that and we get some numbers. And even if we understand how the instrument got to these numbers, which is the whole point, a big point of a lot of the book, right? Even if we understand how the instrument got to these numbers, we don't necessarily inherently think like, what's the quality of this number? It
Right.
might be telling us something we want to know, but what's the uncertainty around all of the parameters that went into this, okay? So we start on that topic in chapter 2, and then chapter 3, we really start to get into some sort of leaf level biology and thinking about like the diffusion of gases into and out of a leaf. So we're starting to connect the instrument to the plant more and more.
Mm-hmm.
And the secondary parameters, as I mentioned, they're all calculated based on those primary measurements. And we talk about not only the situations where you might introduce or have some level of uncertainty in any one of these parameters based on uncertainty in either the measure parameters or uncertainty in sort of biological parts of the system, but also when does it matter? Okay, so under what measurement conditions should I be worried that one of these assumptions that goes into calculating these secondary parameters is maybe invalid, either partially or entirely?
Right.
And so we keep it very practical in that regard, and there's some wonderful plots. And I think chapter 3 is where we really start to shine with some like really useful plots to get at. Like if I just want to go out and make some measurements, what are some really useful things to keep in mind? What are the measurement conditions and where I need to pay more attention to this uncertainty?
Right. And so, yeah, what assumptions are okay, and then if they're okay.
Yeah. When? Under what conditions may you need to worry more about this than others, right? Because we put a whole bunch of assumptions in, and they're integral to deriving these parameters all the time. But sometimes small or even large errors in what goes into the assumption, so the assumption not being met, sometimes that is a meaningful part of the total signal of the parameter that you're interested in measuring. Sometimes it doesn't matter that much because the thing that you're trying to measure is of such a larger magnitude that this parameter doesn't, like a 10% error in this parameter doesn't really matter that much.
Right. And so you've been part of sales, and you're doing a lot of these workshops, and you're teaching quite a bit. What are some, without going too much into the book details and things, but maybe just if you could give an example of when the assumptions really do matter and when maybe not as much. And these are specific, right? These are not broad brush necessarily.
Sure. Well, I can give a good specific instance, something that I like to hit on in workshops. So we include a whole lot of defaults in our system, right? And the first thing I do at workshops is tell people, don't trust any of these defaults if you don't know what they mean at all, right? So we spend a lot of time saying, this is why this is a default. Some of these are reasonable defaults, some of these are not. One of our defaults is the ratio of conductances between the top and the bottom of a leaf.
Yes.
If we have a two-dimensional leaf clamped in a chamber, okay? That specific ratio, we set a default in the system based on sort of a typical leaf situation. Not all leaves have the same ratio of conductances. The only way to know for your specific leaf would be to measure it, and there are ways to do that with our systems, with other instruments as well. But whether some amount of error in that ratio matters for your calculation of stomatal conductance, which is where it primarily plays a role, Whether it matters depends on the magnitude of stomatal conductance. So at fairly low to medium stomatal conductances, it doesn't really matter that much if you're off by a reasonably small margin in this ratio.
Right.
But at very high conductances, a 5-10%, I'll just bungle the numbers here. We have some good case studies on this, but something like a 5 to 10% error in this ratio can end up giving you like 20 to 25% errors in your calculated stomatal conductance to water vapor, which is massive, especially when you're at a really large conductance, right?
100%, yes.
So let's say you're so unlucky that you have to measure gas exchange on a Arabidopsis. Okay, you've struggled for years to get one leaf in the chamber. Congratulations if you make it work, and I'm sorry on behalf of LI-COR if this is frustrating for you. But once you've managed to actually get a leaf in the chamber and start making a measurement, you probably find that it doesn't have very high stomatal conductances. A lot of these little small herbaceous plants that aren't, I mean, it's weedy, but it doesn't have the highest rates of transpiration and the highest conductances in the grand scheme of plants. Okay, which is also something we touch on a little bit in this chapter. So when it has really low conductances, you can have a fairly large offset in what the true ratio of conductances from top to bottom of the leaf is, and it won't really make that big of a difference in the final estimate of conductance.
Sure. Yeah, no, that makes a lot of sense. And I'll try to gloss over the fact that you
just insulted
threw a lot of shade
50% of the plant biology community.
The most successful model species in biology.
It's not the fault of the species that it has small. I mean, it sort of is the fault of the species, but from our perspective, it's the fault of us for not making a chamber that makes it easy to measure that.
You're making it personal, and it's making me uncomfortable.
Well, you are the product manager.
Moving on.
Okay.
Let's you covered some less and more impactful assumptions, specifically with conductance. And we talked a lot about conductance, transpiration, the importance of temperature. And so temperature, obviously there's a sensor, right? There's multiple sensors where we can measure temperature across different locations.
Mm-hmm.
But maybe for those who are new, like very new to leaf level physiology, maybe break down what conductance and transpiration are and how they differ.
So transpiration is a count of the flux of water vapor molecules out of the leaf. Okay, so we've talked a little bit about CO2 fluxes, where we'd say like, okay, this many micromoles of CO2 were exchanged per second from this area, this leaf area, right? So micromoles of CO2 per meter square of leaf area per second. That's how we would start to quantify a CO2 flux and say something about CO2 assimilation.
Sure.
Transpiration is just the sort of the inverse of that in the water vapor side of things, right? If our plant has its stomata open and it is well watered enough that it has some water potential gradient within the vasculature, then the atmospheric water vapor concentration the atmospheric water vapor mole fraction is lower than that within the leaf, and there's a diffusive pathway from inside the leaf to out, then there will be a net transpiratory efflux of water vapor out of the leaf. Okay? Stomatal conductance basically gives us a measurement of how much control the leaf is putting over that process. So the way that we go about deriving this conductance measurement, we end up reporting it in the same units as transpiration, so as water vapor molecules lost. The reason we have to be very specific about this and not just say like use one versus the other is we need to give some context around this, because remember that our chamber measurement is not the same environment as sort of a leaf out in its ambient atmosphere. Okay?
What?
Yes, I know it's crazy, but again, some people will say like, well, can we scale up this transpiration number to say something about a field? Probably not. Maybe though.
It depends.
It depends, exactly. We use a very important term in all of our training in this book called the apparent transpiration.
Right.
Because again, transpiration is a real count of water vapor molecules leaving the leaf, but we have some opportunity by the way that we configure the instrument to impact the diffusive gradient between inside the leaf and out within our chamber. Okay, and that can affect that rate of water vapor transport. By measuring leaf temperature and using that to calculate stomatal conductance to water vapor, we can calculate a biological control over this process that's independent of this potential out of leaf in-chamber humidity gradient that we have some control of.
I would call that an out-of-leaf experience.
Exactly, which is what we're all living, except Jason.
Yeah, I don't know where that
because
guy
he
lives.
thinks like a plant. Thus, he is exclusively living an in-leaf experience.
A very important distinction. Yeah, so breaking down the difference between conductance and transpiration, I think a lot of times people use them interchangeably because they're both about water.
Shouldn't.
And they most definitely should not. But what happens when errors happens? I know there's some minimal, there's some smaller errors and larger errors, but maybe break down the importance of having a quality temperature measure.
So the way we get at this stomatal conductance to water vapor is by making a key assumption that the intercellular airspace of the leaf is saturated. And the way we get at that assumption is by knowing something about the temperature of the airspace within the leaf. Okay, and so the amount of water vapor that a parcel of air can hold at a given temperature is at saturation is fixed, and there's an exponential relationship between what that mole fraction of water vapor is and temperature. And so if we can make a key assumption here that the intercellular airspace of the leaf is completely saturated, then if we can measure the temperature, we can calculate what is the mole fraction of water vapor in the leaf. Okay, and so we talk about in the mass balance section, like how we go about calculating the rate of transpiration. One important part of that is knowing what the mole fraction of water vapor is outside the leaf within our chamber. And so if we know our mole fraction outside of the leaf within our chamber, and we make an assumption, and then via that assumption know what the mole fraction of water vapor is inside the leaf, which requires that temperature measurement, then we can calculate how easy is it for diffusion to occur. So what's the conductance between inside and outside of the leaf?
I mean, that's amazing.
It's fairly simple. And so for the most of our measurements,
Here
this
I
is
say
presumably
amazing, and you say simple. Welcome to the difference between a scientist and a product manager.
Yeah, you're a scientist too, though. So the importance here is that if you're off in your temperature measurement, which is sort of a fundamental part of this stomatal conductance to water vapor, then you potentially could be wildly off in your conductance calculation. Again, we give some nice plots and information in the book about how far off you might be in different situations.
Yeah.
But it's important to know that temperature measurements is critical for this. And then from the stomatal conductance to water vapor, we also end up deriving conductance to CO2. And then we use that to estimate the intercellular CO2 concentration. Okay, so again, no sensor inside the leaf, but we can say something about, with reasonable certainty, if the assumptions are met, we can say something about what's the mole fraction of CO2 inside the leaf, which is pretty neat. But
that's why I went to grad school.
If this assumption of saturation, among other things, if this assumption of saturation is not met, like say you have a leaf that's losing turgor pressure, and there's increasing evidence to suggest that like the leaf intercellular airspace is not always saturated, there has to be some gradient, otherwise there would be no transpiration in the first place, right? To the extent that that matters for these calculations depends on how big that level of, like what magnitude of unsaturation we're facing here. But if that assumption is not met, you potentially could see very large errors in this calculation of all of these conductance pathways, and then you could underestimate the intercellular CO2 concentration. Why that matters, we talk about in later chapters when we talk about like what do you actually do with these numbers. People like to fit some response curves to the response of CO2 assimilation to this intercellular CO2 concentration. If you don't know what the intercellular CO2 concentration actually is, it's not going to be very meaningful for trying to derive some parameters from that relationship.
Absolutely, yeah.
And we use those types of relationships and those parameters to tell us something about how the world works. Like these feed into climate change models.
Yeah, the importance of making sure that you are collecting accurate, well, let's just say, if I'm collecting adequate data and other people are collecting expert data, like you're completely right. This is not a one-off instance. These are directly fed into global change models. These are the data that you're collecting at the leaf level does have a huge impact for the plot, for the landscape, and at continental scales. Well, now that I'm kind of done patting myself on the back with all that we do here at LI-COR, we're coming up on time. So maybe if you could summarize not only what we've talked about here, but maybe what readers should expect. So essentially just take the last 40 minutes and just actually just give people the nitty-gritty.
Sure, I could try to do that. You were sufficiently serious about this climate change. You've probably scared everybody who just wants to take some assimilation measurements on their different plots of soybeans. So
the weight of the world and global food security is on your shoulders.
Yeah, good job.
You feel better?
It'll be okay, though, because you have this book to guide you, and you'll make great measurements.
Fear not.
And then when they're brought into some random meta-analysis, you'll be ready to go.
Yes.
And appropriately cited. Yeah, so these 2 chapters, though, I think from chapter 2, like I told you, I get excited about uncertainty and telling people, like, hey, you should think about uncertainty.
You sure about that?
I'm sure about that, yeah. I live a life of constant uncertainty, and I like my gas exchangers to do the same.
That's gross.
Yeah, so I think some key takeaways from this, like, we want you to recognize that the things that we're measuring, we're only measuring a few basic things, and we're making a whole lot of calculations based on it. So there are a lot of opportunities for propagation of errors and uncertainty and parameter estimates. And it is, as much as we try to build guardrails onto these things and instruments to sort of make the measurements as accessible as possible, and we do continue to do increasingly well at that. But as much as we try to do that, there are still opportunities for you to sort of misinterpret what certain numbers mean, what's the difference between an input and an output in the system, and then potentially that leads to erroneous conclusions in the things you're interested in. And even if it doesn't feed into a climate change model that changes the world, maybe it makes it really hard to collect useful data for your PhD. That's a real bummer, right? So having some understanding of what actually goes into these measurements is quite important to getting meaningful data, okay? So thinking about measurement quality is a big part of this game, and there are some things we can do with the instruments to improve measurement quality. We give you a nice, I won't say list because it's not just a bulleted list, but we give you a nice set of rules of thumb and ways you can go about ensuring that you get the highest quality measurements.
Yeah, that's great. Thank you so much for walking through all of this. Thank you for joining me sitting here in this fairly, I don't know, what would you call this room that we're in?
A former garage or garage.
Yeah, former garage,
if you will.
Yeah, so thank you for sacrificing some of your day. Is there any last thing you want to tell the listeners here?
Yes, there's one thing I want to tell the listeners. It's that ferns matter. And I want to tell you that it's not a sacrifice. It's been very fun hanging out with you today, and I hope we can do this some more in the future.
Thank you very much, Dr. Richard Vath. Well, thank you for being here for episode 2. Remember to like and subscribe so you do not miss an episode. And if you are attending ESA, swing on by LI-COR and Hobo's booth, 801 to 803, to tell us what you're working on. Until then, stay curious, stay kind, and I'll talk to you soon.